lots of things. So, and it moves all over the place. Normal's always just going to look like that whole thing, and they do this, and they slide around each way. But betas do all kinds of neat stuff. Okay, let's get started with Bayesian prediction. So some people call this forecasting. There's a lot of things that you can call it. Basically, the name of the game is to find a distribution on the thing that you're uncertain about and condition on the stuff that you know. So that's what a Bayesian's always doing. So Bayesian will always condition on the data that they've seen, and they'll put the probability distribution on the thing that they're uncertain about. Now you might say, isn't that what everybody does? But it's not. It's not what a classicist does. So classicists built their distribution on the data that they observed. And they talk about the randomness of that, and they use that as a proxy for talking about theta, which is conditioned in their equations. And then if they want to come up with a function over theta, they usually do a pivoting type argument. Very different. So Bayesian is flipping the conditionals from the get-go and putting the explicit probability distribution on the thing they don't know. So imagine you see some data, x, x1 to xn, and you want to forecast the future. The future we'll denote as x tilde. So that's really the name of the game. Now, what I'm about to tell you generalizes to the non-IID case trivially. And so what I'm about to show you and how to do it, it extends quite naturally. The example I'll show you will be an IID case so that you can compare to something you're probably already familiar with. We'll get some intuition. But really, to come up with this right here, we need to take into account what we know. We know the data. We probably know the model. So let's just consider the IID case. Let xi's come from this model. Basically, what we're really doing when we're forecasting is we're trying to learn the thetas in that model, and then in some sense, we want to capture that uncertainty over here and then use this distributional form to tell us what the future x looks like. And so if we knew what theta was, if you gave me theta, and I was looking at something that was IID, I would just sample from this distribution. What do I think the future looks like? If I had to guess, I'll just sample from this. Or maybe I'll look for the expectation of this distribution, some good centering parameter. So, but basically, the future always is going to have this inherent uncertainty to it, whatever's governing the process in the first place. And all we can do is pin down our certainties about theta. And so, Ben had come to me at the end of the class last time and he said, is this what a Bayesian does? Usually I probe you guys for a little while and say, how do you get this distribution? But the reality is you just look at what it says. I want to know what x tilde is, and I want to condition on the past. Now in my IID example, these are conditionally independent of each other. But of course, theta's tying them together. So that's the bridge here. How do we get this? I usually just follow the math. I know what this distribution is, right here. We want, really, fx tilde, the future, given theta. That would be our ideal goal, but we don't know theta. So how do I get rid of the presence of theta in this equation? I just integrate it away. So if a parameter is leaving a Bayesian's equation, it's because they've averaged over it. They've averaged it out of the equation. There's really only one gig in town. And so Ben, when he looked at this, he said, do I just do this? It's the first time in quite a few years that somebody's just come up with the answer. That's the answer. So that's what we do. So again, I know what theta is. I know how to condition on the data and get thetas, and then I'm going to average out this theta. So this is really just a weight. This is a belief of theta. If I knew what theta was and I just plugged it in, then this would represent a point mass on theta. And that would be equivalent to that. And if I don't know what theta is, maybe I want to be a little uncertain. What I have seen people do, I've observed this, things of this nature. So I've seen statisticians do stuff like this. They'll say to predict, maybe you do this. I'm going to say, I'm going to look at this distribution. I'm going to look at fx tilde. So x tilde is just a dummy representation for the future. Don't know what it is, so I'm putting a distribution on it. And maybe I'll plug in my best guess at theta into there. So this is my best guess. Or best inference. So imagine you're a non-Bayesian, and I know that's getting harder and harder to do as this class progresses. But maybe I get the NLE, and I just drop it into that equation, and I say, hey, that's a good forecasting distribution. I've conditioned on my best thing. Now that's a really unsatisfying answer because I don't know uncertainty about thetas. If theta was something that I was really certain about, I think this is a pretty good solution. However, if our inference is about theta, maybe we're really uncertain. To a Bayesian, that would mean a diffuse distribution. This doesn't have all that uncertainty built into it. And so what I've seen people do, and I don't do this, Bayesians don't do this, is to include uncertainty by doing something like this. You might do something like this. I'll say fx tilde, so I'll look at this distribution, and I don't quite know what to do, but I've seen a lot of people always say, well, maybe if the parameters come from an exponential family, maybe I think everything is asymptotically normal. It turns out that happens in parameters in exponential family distributions. Is usually their inferences limit to a normal. So they'll say, okay, well, I'll just do plus and minus. So I'll look at two different versions of this. I'll multiply by 1.96, and then I'll look at the standard error for theta. This is the standard error. Okay, so variability in theta hat, how uncertain there will be about it. So people do this sort of stuff all the time. I've seen my colleagues do it, and I'm always kind of like, you think this is a 95% interval for your prediction. Why? Well, under some conditions and blah, 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 maybe this is a good approximator. And it's really kind of hand-wavy to do this. I didn't follow real probability rules. I used some sort of a heuristic and carried it through the analysis. And I don't know if that heuristic really carries over. And so I don't think this is a good solution. I don't like this, but it kind of smacks of doing this right here, where instead of just plugging in 1 point, I'm plugging in 3 points. So basically the plus and the minus and that 1. And so I've got some sort of idea that if I move theta, what would my predictions look like? So I move theta a little bit and I see how my predictions perturb. The Bayesian's equation does all of this simultaneously. So, and it's going to include the whole continuum of points. I've written it down as an integral, so we can think of theta as a continuum. If it's discrete, just change everything to sums. But this includes all the uncertainties. So this is just a weighted average. So I'm going to write this down as a weighted average. Of these functions, f, x, given theta, with weights, pi theta. all these integrals are some form of a weighted average. That's all statisticians are playing around with. We're weighting by distributions. And so we try to figure out what those weighting functions are. But I think this is a very good answer. It kind of propagates all that uncertainty through. It's a covariant probability rule. You might, of course, go back, how did you form this, and get back into issues of the prior, because we must have a posterior there. How did you form your posterior? And those are all relevant questions. Hopefully, by the end of this class, when you pick out a prior, you have good defenses for why you like it, and you can demonstrate to people that it has good properties. And you could even show them, if you changed the prior, what the impact of that was and how it might influence your analyses. So I like to do everything for my clients. I'll show you everything, the choices I made, and I'll try to convince you that they're good choices. And I probably won't talk about eigenspaces while I do it, so bring down the language a little bit. But anyway, hopefully this is intuitive to you. I really like it. This really is the Bayesian solution. We do this every single time. Form the posterior and just average over it. Let's look at the non-IID case. It's very similar. So non-IID.
Is that not supposed to have the x tilde?
What's that?
You said it's the weighted average of fx theta.
Oh, which weights?
No,
So,
it should be x tilde, right?
oh, yes. Thank you.
There.
That's it. That dummy variable for the future. Absolutely. I lost my train of thought. Where did I say I was going?
Non-ID case?
Non-IID. Yeah. So non-IID, let me give you an example, okay? So I don't have to butter up the notation a lot to tell you general things of things that I could do. I'll give you something explicit. So in all the examples, we'll extend like this. Non-IID example. I have to tell you the mechanism of dependence. I have to model that. That has to be explicit. And so imagine I did that, and I knew a good model, and I was able to figure out all the dependencies. Let's say that for my problem, the dependency looked like this. So I'll say that the xi's are related to each other through this equation. Theta xi minus 1 plus air. We might say that this is normal. These are all building blocks for coming up with more sophisticated dependencies. This is an autoregressive one model. And you might say, hey, there has to be some limitations on this thing if you're going to infer it. We'll probably say theta is bounded by 1, the modulus of it. That makes it so this model actually has good probabilistic properties. It's stationary when we do that. And so this is just a regression model, but I can't tell you what the xi is. I can't just draw it without telling you what xi minus 1 is. And so that's what this equation is. And so the only thing I have to do is I need to model this dependency. And I'm going to have you play around with this model in the future. Maybe this is homework 3. You'll get some experience in writing down these likelihoods. But basically, I just need to form the posterior, just as we did before. So step 1, form the posterior. For theta. And I'm going to assume, as I've been assuming, this is unknown. This one's known. If I didn't know sigma squared and I had to infer it, it would change this into a t regression. Okay, so it would change my errors to t. And so I need to form the posterior. So I need to understand properties of theta and come up with some good prior for it. Let me just ask you guys. Any suggestions on priors for theta? You're just thinking regression. Okay, so this is just regression. This looks like y is equal to x beta, but I've changed my y's to x's. What's that?
Normal.
Normal. Might get something good out of normal. It turns out it's conjugate in this case. So t, maybe you want to put some heavier tails on there and convolute my mathematics, make my life harder, but probably won't hurt us to do that. What's that? Gamma would be a big assumption about the positivity of that parameter. So I haven't really said that it's positive yet. I did write it down an absolute value sign, implying that it could be negative.
Then uniform.
And maybe uniform, yeah. And maybe I would even restrict it to the stationary range, that constraint. The reason that that's there is imagine theta was 5. So if I had xi minus 1 was 1, I multiply it in, I jitter it with some noise, maybe the variance is small, so this is going to be about 5. Now I take 5 and I plug it into this equation, 25. 125. Big numbers are coming up. This equation will explode on you. And so it doesn't have nice stationary properties. And so maybe I would invoke stationary, but I better check. You know, if I put a restrictive prior and just see if it's in the stationary range. But maybe uniform right in there. Keep in mind, theta is acting as a shift. If we consider xi minus 1 fixed in this equation, but it is. Everything on the right-hand side is always fixed when we're generating the next thing. So this is acting as a shift with respect to its covariant. So maybe uniform. All good answers. So normals probably wouldn't hurt you. Make them kind of diffuse. T's probably not going to hurt you. So probably get pretty close answers. So we could do a sensitivity analysis on how well we did. Of course, if you ended up tightening up those T's and normals, we could get very different answers. But I bet we'd get very similar answers.
Can we have an improper prior here?
Well, if I wanted to
If you really wanted to.
adhere to the bound, then I would use a proper one. But it turns out what I always do is I always include an improper prior and let that be across the whole region. And if I detect the parameters trying to jump out from my bound, I usually build a new model right there where it starts breaking the bound. And so that's called change point modeling. And there's a lot of variants that you can do to do that. But let's just keep it simple. But yes, the answer is you could use improper prior. And I would.
Wait, so when you say improper, do you mean something that would not be integrable just on -1 to 1?
Yep.
So like.
Oh, but -1 to 1, yeah, exactly. It's that would be really weird to build an improper prior there. I would never do that. So I
So
mean
you
over
mean
the whole
improper in the
continuum.
sense, right?
Yeah, I would not build like some weird thing that was like asymptotically shooting up at the ends. That would be a really weird prior to use on this problem. The way that it's set up, bless you. So lots of possible choices. I think all your choices and recommendations sound about good. So form the posterior. I've got some prior. So given prior, let's just say flat, probably what I would do for the nature of this problem because it's a shift. Then I would build my posterior. So my posterior distribution,
But this is improper, right?
I chose improper. So I'm just saying it's improper. Again, we're just entertaining choices. I've chosen one. I wrote it down. Make my math easy. And so this thing right here is going to be proportional to the likelihood, given all of the data, times my prior. Prior is not going to do anything, at least the one that I've decided to select out of all your choices. So I just need to write down this likelihood, and this likelihood is not just a product of things, but you have to condition appropriately. Really what this looks like is just this. I condition, so they're conditionally IID. So let me ask a question. Is this xi independent of that xi minus 1? It depends on how I phrase that question. You guys are right that absolutely they depend on each other, so marginally they depend. But let me ask this question. Is x3 independent of x1? So this is a slightly more complicated question. Because when I get x3, I don't plug x1 into the equation.
But you plug in x2.
x2, which depends on x1. So there is some dependence right here. So the answer is no, but given x2, it's conditionally independent. So when I say conditionally independent, I don't mean it's independent. I mean there's things that I need to know, and if you told me those, then I don't need to see that thing. And so if you tell me x2, I don't need x1 to generate x3. But conditionally independent and independent are very different things. We never see independence in real data.
It's the initial condition for this recursion.
Yeah, exactly. So what would I do as a Bayesian if I were trying to do all of this? I would just start at the first data point and say you were given that. Possibly. What Bayesians do if they need to interpret, like, and they want to be in, like, have some flexibility, is they might put a prior on x0. That's a very typical thing to do. So put a prior on x0 and then you can start running this. Just write that down. Very typically, not everybody. As a Bayesian, we might write this down. Put a prior x0. So I have some density on x0, and I'm willing to entertain starting conditions. You will see engineers do this, and they won't say it as a Bayesian thing. They'll just say, hey, I reran this at lots of different starting points, and I averaged my answers together. Now, did they follow the proper Bayes rule to do that? Maybe, maybe not. But if you do this and treat it as a Bayesian, you probably did something coherent. Of course, knowing the range of these things can be difficult in practice. Some people just start with the first data point. If it makes a huge difference, you probably don't have enough data. Okay, so this thing right here is just going to be a product. I goes from 1 to n, and I'm going to write this model down, give us some notation. This is going to be f xi given theta xi minus 1. And if you'd like to write down the sigma squared, that's fine too. I'm saying that it's known. So I'm just going to drop it. And so this would be f xi given xi minus 1 and theta. Now, I have to be a little bit careful of where I start from and take into consideration what Ben just said. Let's say I have an appropriate starting condition. Maybe I just plug things in and I offset everything and I start from the second data point. That's another possibility that we just talked about, so I'll just make my life easier. Normally I'd place a prior. We could do this. You do see people do this all the time. I usually argue if it makes a big difference, you don't have enough data. It's unclear what to do in these cases.
Why did you start at 271?
Because I need to start somewhere. I don't have a distribution for 1 without 0,
Oh,
right? There's this dependence and this Ben's question of how we start this thing. So I'll just say we fix the first data point. It gives us a starting point. Make it more complicated and build prior in on it. Choose not to do it. So that's our likelihood function right here. So we're just building in these dependencies. For our normal model, this would just be written down like this. Product I goes from 1, or from 2, we'll say, to n. I know the sigmas, I don't need to write them all down, so I'm just going to write down e to the minus xi minus theta xi minus 1 squared over sigma squared, which is my likelihood function. So I'm done. So I get my likelihood, and then I multiply in my prior, and I figure out what my posterior is. Does anybody know what resulting posterior is? So the posterior that we get from this analysis, what do you think it is? What distributional family do you think it lives in? This is an easy question. It's normal. It's got to be. I'm using an improper form of the conjugate prior, so it's normal. And so this would be subnormal. And then there would be some parameters in here that I need to estimate. So I need to know what these things are. I'll give you a hint. The answer is there in disguise. So if you re-encode the y's is xi's, and the x's is xi minus 1 vectors, then this equation just lends itself. So turns out if we ended up calling this x, and I'll write this down as I, is just equal to this vector right here. This is going to be x, I'll say 2 down to xn. And I'm going to write down x I minus 1 vector. And this is going to be x1 down to xn minus 1. Okay, so now I have some representation. The answer is this. So the posterior mean is going to be x I minus 1 transpose x I minus 1 invert. Hopefully you recognize this as all I'm doing is squaring the elements in the vector and adding them together and dividing by that. So this is the step 101 form of regression equations. Times x I minus 1 transpose times xi. So that's the regression equation. So if those equations don't look familiar to you and you can't wheel them quickly, you'll get plenty of practice in this class. In one of my classes that I taught in for the last several years, classrooms, some student had put that up on the corkboard, and you could see that they were just cheating for an exam, writing this down, and it's like, you can't remember that, you're already hosed. So I decided to deliver that to all my students. They can have it for now until the end of time. So, but this is really just that, this is acting as the y. Right here, that's these things. Right here, the xi's and the xi minus 1s are those. So, how do I figure that out? Well, the same way you did it on your homework. Exactly the same thing, is I just work through everything, I find the quadratic term, I find the minus 2 linear term, and I can recognize both the posterior mean and variance. Does anybody know what the variance is right here? So this is just xi transpose xi inverse sigma squared. So regression equations, and you would have come up with this stuff on your homework. That's the non-IAP case. So I have to model the dependency, but the likelihood feels very much the same as we did before. Now how do we do prediction?
It would
Okay,
be I minus 1, right? Not I. You said xi.
I minus 1. Yeah. That's why I like to keep it as x's and y's sometimes in my notation, but yes, those are the xi minus 1s for the variance. Okay, to do prediction, after we do everything, to predict, then what we're going to do, so this is going to be some future observation, but it really is tied to the past somehow. And I've got this past, and I'm going to say this thing is just an integral, and all I have to do is write down this sampling mechanism properly. So fx, I know what the last thing was. I'm going to try to forecast in the future. I'll call it this, given whatever the last data point was. So this is going to be x, I'll call this n plus 1. That's the future. So usually I call that x tilde, but it has an ordering imposed by the auto regression over there. I plug in xn, what I had last time. That's something I get to use to forecast, and I get to use that equation. Sigma squared also goes in here, if you will. Guess I didn't write it down before, so have to get rid of it, and we have the theta in our model. And then I take my posterior that I just got, and I do the exact same thing. That's Bayesian forecasting. Just model all the dependencies, make sure they're in your equations. So, and then we just go to town. So again, all we're doing in both the IID and non-IID cases are just averaging over our posteriors. So if you've ever taken a Bayesian time series class, you're quite familiar with this. If you've ever taken a filtering class in EE and you've seen Kalman filtering, this is what you were doing. So you were doing this sort of stuff. So in the forward filtering and backward simulation, this stuff happens. So for me, guys like me, I always see that and I go, oh, it's Bayesian. Bayesian sequential updating, that's what you're doing. And some people say it's something different. It's okay. Okay, so let's go through a real example. Go back to the IID case and see what we can work out. Any questions before we entertain an example?
I'm a little confused as to why we have a vector-based posterior when we have a scalar-based.
It wasn't supposed to be. So if I ended up looking at this equation right here, x transpose x inverse, so these were I minus 1s, transpose, these were the I minus 1s. That's a scalar right there. And then this was the I minus 1 and these were the i's. This is a scalar.
Okay.
Yeah, but good dimensionality check, always good to check those things. Stat 101 classes, they have you derive those totally differently. I just like people just go to the linear algebra because now you've got every dimensional problem. Can't remember all those formulas, those sums of squares, but you can't remember that. Okay, so example. Working through that integral might be a little bit more challenging than the integral I'm about to work through now. So that's why I like doing the IID case, because I can actually do it in a reasonable amount of time. So let's say xi's are IID. Normal, mu, sigma squared. No surprise, we'll go back to one of our favorite distributions because we have a lot of intuition about it. We've seen this distribution used in problems and examples. Using normality, we'll see how the Bayesian answer compares. I'm going to say I know this, just to keep the work on the board pretty clean. If I didn't, everything would change to a t-type analysis. And so I want to infer that. I'm going to take a prior from you. I'll pick my flat prior, keep my math simple. If I had knowledge that I wanted to inject, I might entertain the full-blown normal thing. I'm going to say I goes from 1 to n. And our goal is to find this distribution. This distribution has a name. It's called the posterior predictive distribution. So that's how Bayesian does inferences. They do it off of the posterior predictive. How do they get it? They take their sampling distribution, they multiply by their posterior, integrate over the parameter space, which is really just a weighted average of the stuff you don't know. It's nice when you're a Bayesian because all your probability rules, if you understand your probability rules, and I'm pretty sure that's what Ben's doing over there, is just following probability rules. He knows what Kolmogorov taught him, he uses those rules, and you follow the whole analysis through, and that's what a Bayesian is doing. So everything just lives in a probability space, and we operate with the same rules and not heuristics. So what we need first, step 1, is we're going to need to find the posterior. Pi mu given x. I think we know what this is. Somebody please help me out.
Normal.
Seems like when I give you the child's play questions, everybody's too bashful to answer. This makes me look like a jerk up here. What is it? David, I know you know. It's normal. Where's it centered?
X bar.
Got it. Entertain you with these things, so just let it out. Can never tell if it's you don't know, and I got to explain this again, or it's just too easy. Usually I can tell by the smirks on people's faces which one is which, and David's a good giveaway, so thank you for that. So we know this, we worked it out before, answer that's quite appealing to us, and now all we have to do is find this. X tilde given x is just going to be equal to our fx tilde given mu pi mu given our previous data. Integrate over mu. Of course, we'll be doing this over the whole space that mu lives. And so we just need to work through this equation. So write down these distributions. 1 over root 2 pi sigma e to the minus 1/2 x tilde minus mu squared over sigma squared. And then this one right here is just 1 over root 2 pi sigma over root n e to the minus 1/2 mu minus x bar squared over sigma squared over n. Mu. So we just need to integrate those two things. Of course, we don't need the normalizing constants. We get rid of those. I know sigma. If I did throw those away, and I didn't know sigma, I would have made a big mistake. And so really, this is just an exercise in calculus. So we need to find integral negative infinity to infinity e to the minus 1/2 x tilde minus mu squared over sigma squared e to the minus 1/2 mu minus x bar squared over sigma squared over n mu. So just an exercise. Turns out this integral is a little hard to do if you're under-experienced with it. And so if you didn't know anything, you'd probably go ask somebody, if you went to the math department, they would say, go do it in polar, and you would get the answer. Keep in mind that our answer, because I dropped off all of my proportionality constants, this is just up to proportionality.
If we add and subtract x bar, does it have anything in
You do need to complete the square probably to do this problem, but it's not going to be x bar in here. There's going to be some other thing that this thing centers around. We have two pieces here, so we have to be a little more careful with that. And so I always hate doing this because it takes about 10 lines to go through if I go through every step, and it's very algebraic. What distribution do you think this follows? We'll just ask this question. Which disk do you think this follows?
Normal.
Absolutely. It's normal. How would you convince yourself of that? You'd have to convince yourself that the form of this thing after I did the integration was e to the minus some quadratic form in x tilde. So you could probably chisel your way through this until you recognize that that was never going to go away. And that does happen, but you have to convince yourself of that. I will tell you, when you take these Gaussians like this and you multiply them in and you integrate over the parameter space, it's always normal. It won't change. And so it is every single time. So once you do it once, you know it's normal. So I'm not inclined to do this in 8 minutes, but I'll show you a shortcut for doing this. So we know it's normal, or at least we believe that it is. Some of you might not be convinced. I think doing this integral next time, we'll start class with it, and I'll already have the steps written down on the board. You guys can take a picture of it with your camera, or whatever you choose to do. But I think I'll go through the steps, have it carved out on the board, so if you want to show up a minute or two early to have a look at it, we'll walk through the steps and see that we get the exact same answer. But in general, you need to work through this integral to recognize what the distribution is. However, if you recognize the distribution and you say, all I need to do is identify the parameters of that distribution, in the normal case it's an expectation and a variance, that's an easier problem. And so, we need to find expectation x tilde given x and the variance of x tilde given x. Without showing it, we think x tilde given x is normal. It is. We can verify that next time. But if I did know that it was normal, all I got to do is find these expectation and variances. This is actually pretty easy to do. Does anybody know how to do this in 1 or 2 lines? This is a hierarchical model, so let me just help you out. Every Bayesian model is a hierarchical model. What are the hierarchies? Posterior sampling, and then sampling out of the original sampling distribution. To be more clear about that, you can actually exploit that in an algorithm. Just do this subsequent sampling, inform through a Monte Carlo solution what this posterior predictive looks like. I do that quite often, so that I don't have to do this integral. But this is a hierarchical representation. So your old inference books tell you expectation formulas for working through hierarchical models.
So it should be a weighted sum.
Child's play. What do I need? What's that? Got x theta. Okay. We're doing this mu problem. So we're working on this problem right now. Let's get rid of this.
You do two expectations.
Yeah, iterated expectations, right? So, Annie knows. I know these formulas. So expectation of the expectation of x tilde, I'm going to condition on something right here. And so I can condition on anything I want. So I'm going to just write down some random variable. Anything I want, that's just a placeholder. So given x, right here, and given x. That's true. I haven't told you what happy face is, and it's pretty useless in this problem if I just have some other hierarchy that I'm shoving in here. But that's always true. So just recall that expectation, and this is just a generic formula, is the expectation of z given some other variable. And I'll just write down x, if you will. What is this expectation over right here? This is over whatever this model is, z given x. And then what is this expectation over? It's x. So that's what we do in all of this, is we do that conditioning. Could you prove this if I asked you to do it? It's super easy. You write down the left and right hand sides and show that they're the same, and you'll use Fubini's to flip around the integration. And so just write down the left and right hand sides. Instead of doing this right here, I'm going to plug in something that I know that tells me about the model. So I'm going to use my hierarchical representation with mu. In general, that formula is always true, but I'm going to plug in the thing that I don't know right here. And then I'm going to go to down. There's a similar formula over here. This is variance of the expectation of x tilde given mu in x, condition on x. As soon as I condition the left-hand side, I need to condition all of my operators on it. That thing's fixed, we get to know that all the way through. So that's why I'm conditioning on x, and I'm conditioning on x. This is plus expectation of the variance of x tilde given mu and x, cap x, condition on cap x. And then I just need to work through these things. Let's go back to the expectation. Somebody help me out. What's this interior expectation? Expectation of x tilde given I get to see mu and cap x.
Mu.
It's mu. Data won't help me if I know mu. I already know what the expectation of this thing is if you give me mu. And so this is going to be the expectation of mu given x right here. And now I just need to work this thing out. What is this? This is a posterior distribution. So keep your notation so you understand what these things are. What's the expectation of mu given x? It's x bar. So the posterior predictive distribution is centered around x bar. No great surprise. Where else would you center this thing? So we could have done a lot of math, completed the squared, looked for -2, linear terms, quadratic terms, walk through this, come up with the exact same answer. Let's just work through this one. This is the variance of x tilde given mu. Well, I know the expectation of that thing, that's mu, we just answered that. So this is the variance of mu given x plus the expectation of the variance, sigma squared, given x. What's this? Yeah, there's something I haven't written down all the way through this in that I know sigma squared. And I usually tell people, write down in all your notation what you know. You actually know sigma squared already. So this notation isn't quite telling us that, but we know it. And so what I would normally do in all of this is I would condition on sigma squared, I'd condition on sigma squared, I'd condition on sigma squared, and I would condition on sigma squared. And it would remind me throughout the problem that I get to know it. So this thing is going to be sigma squared over n. But what about this one? This is where the notation really helps you.
Sigma squared.
It's sigma squared because I know sigma squared. So if you didn't write that down, you might be inclined to think that's a posterior estimate. But it's not because you have knowledge of sigma squared. So this is sigma squared
Why is the first one sigma squared over n?
because that's a posterior. I get to know all the data. So that's the posterior variance that we worked out. So let's look at this. This right here is the variability that's inherent to the problem as it is. Our forecasted sample, if I told you what mu is, has variability sigma squared, and you can never get away from that. And so this variance right here is inherent to the problem. This variance right here is coming from the parameter estimation, and that you can drive down towards 0. So in forecasting, there's always something that's inherently variable. It's what the original distribution looks like. That inherent sampling mechanism is creating stochasticity in your answer, but your parameters you can drive down what their variability is. So I like this answer, and this is probably an answer that we're familiar with. And most of my classical friends would come up with this as an answer. So predictive intervals, if you've ever done predictive regression, you have something just like this. It's kind of intuitive. Come back next time, have a glance at that integral, because for other problems that you aren't so in tune with, you might not recognize the distribution. You have to do a little bit of work to figure out what the whole thing is. So that's it for now, guys. What we will be doing for the next couple lectures is changing all the examples and doing the exact same thing, so that we get in step with what a Bayesian does. Kind of nice, I've told you everything you need to know about Bayesian prediction except working through all. It's always that. Thanks, you guys.